Hi, my name is Geoff Raifsnider, and I'm a Senior Mechanical Engineer with GFS.
And I'm Brian Schadrie, a Senior Mechanical Engineer at GFS as well.
Today we'll be covering a special category of spray booths, recirculation booths. These are the spray booths that return the air that has been exhausted during spray operations back to the booth. Now, these are different than the spray booths which may include a cure mode where the air is recirculated while it's unoccupied. We'll save that product for a possible topic for another session.
With recirculation spray booths, what we were going to outline today is we're going to go through some diagrams on airflow to confirm, verify what we're talking about as far as the differences between conventional and recirculation spray booths. So the first slide is the conventional style spray booth, where we condition the air and it is inserted into the booth, pulled through the working space, filtered, and then exhausted outside. So basically with this style system, the air is brought once through the system and exhausted. Next is a diagram on a sample of a recirculation spray booth. That basically is the same as far as flow in the booth, but in this case, a significant portion of the air from the spray booth is recirculated back to the system. And what that allows is for us to bring in less makeup air and exhaust, and therefore benefits of that was less heating requirements and cooling requirements. So basically what we have is the same flows with the recirculation booth in the working space as a conventional, but the added benefit of conditioning less air and the user using those cost savings to their benefits. The recirculation spray booth again has the same airflow as the conventional for effective overspray capture. It has the pressure control as the same, and like I said, makeup air and the exhaust is typically 20 to 40% of conventional systems. Next I'll be weighing the benefits of recirculation booths versus conventional. This chart shows where conventional and recirculation booths would be best applied. So going through this list one by one, overall airflow and overspray capture, like I said before, conventional and recirculation are equivalent. Booth pressure control, they are equivalent. When we talk about heat up time and paint cycle time, basically what that means is does your process require cycles between paint and cure, multiple a day? Maybe there's several a day, upwards of 2 to 3 to more a day. Conventional systems work typically better for that because they can react fast to changing temperatures from a paint environment to a curing requirement. So that goes in line with cycle time between paint and cure, and then also with curing at higher temperatures. Conventional systems will heat up those spaces faster because again, you're conditioning the whole airstream versus just a portion of it. But then we get into the benefits of recirculation. With that, you have finite temperature control, meaning you can really zero in on specific temperature, plus or minus 5 degrees, for instance, in the booth. Make a slight adjustment, and make a slight adjustment to 20% of the air versus all of the air is going to give you a lot better control. Filter efficiency is higher with recirculation primarily for safety reasons, and Geoff will be discussing that. Longer cure cycles, where the process requires several hours of operation, would give benefit to using recirculation, because that type of system reacts similar to an analogy of a flywheel, that you're conditioning a certain portion of the air, and it takes a while for things to get up to that specific temperature or cool down, vice versa. So those systems which have a long cycle time, recirculation would benefit from. And those typically could include conveyor systems, high production systems where you're operating more than 6 hours a day, robotic systems, non-manned spray booths. Those are all systems in which the company should consider recirculation. Systems greater than 30,000 CFM of total airflow, and then systems that would need VOC abatement. Those types of systems cost a lot of money per CFM, and what recirculation does is allows the process to treat a small portion of what a conventional system would. Secondary benefits are that with recirculation, you're environmentally conscious as far as not needing to heat or cool and use electricity or gas to the level that you would for conventional systems. So the benefit of that is lower operating costs. So you can incorporate and use that savings towards investment to your facility. So to evaluate these systems, we take a look at the operating costs, because that is the biggest benefit from recirculation versus conventional. But to determine those operating costs, we need to look at different specific items within your production. Specifically, where's your site, because it's all climate based as far as the amount of heating or cooling that is needed, the hours of operation, looking at your cycle times, looking at the modes of operation, how many hours a day are you running paint versus curing, and what those temperatures are. So with that type of information, we can really evaluate if recirculation is a viable option. So what I've done now is I put together a summary of some example of some savings opportunities that recirculation can bring to your process. So what I looked at is similar paint booths in locales such as Dallas and Chicago, and looked at 3 different size systems: a 10,000 CFM airflow through a booth, 30,000 CFM, and 100,000 CFM, to give you an idea on the scalability on savings that could be had by each of these types of systems. So what I did was I took each of those sites and we did a conventional and recirculation system. The first slide on energy is a bar chart that shows the operating cost per hour per 10,000 CFM of your system. So on the left, you can see on the conventional system, Dallas and Chicago are on the left. It's showing the cost per hour of spray, economy mode, and cure modes. And you can see that there's a significant difference between Dallas and Chicago's operating costs. That's primarily what that's due to is the climate. Chicago is colder. It's using more energy and more gas cost for that. So what this is showing, and I just want to be specific on this, is it's showing the heating. It's a heating only style spray booth. We didn't consider cooling or dehumidification or any other things besides heating. So this is an analogy of a system that would maintain 70 degrees for spray mode and 120 degrees in cure mode. And they're 80-20 systems. So when we get to recirculation, that's exactly what you see on the right, where you see that the cost per hour differences are substantially less because of recirculation, no matter which site you're at, Dallas versus Chicago. But if you look closer at the recirculation side on the right side, you can still see Chicago maintains a little higher cost of operation, primarily due to climate. The next series of slides, like 3 slides, are basically peeled apart the mode of operation. So I took a look at if these same 3 booths, the 10,000, 30,000, and 100,000 CFM booths, were operating 8 hours a day in paint mode, this would be the energy saved per year for recirculation for those sites at those booth sizes. So you can see at a 10,000 CFM booth, you would save between $2,500 and $4,000 a year in energy by utilizing recirculation during paint mode. And then the savings continue to rise as the volume of air you're moving increases. So you can see it becomes a substantial, by the time you get to 100,000 CFM system, you're saving in Dallas $17,000, $18,000 a year in energy, and $35,000 a year in energy in Chicago. The next scenario shows those same booths operating 4 hours in paint and 4 hours of cure per day. Same analogy, little higher costs because now we're mixing in cure. That cure temperature is 120 degrees, and so overall that average energy cost is more, but with recirculation, what you're seeing here is you're saving more a year because you've incorporated recirculation. And then the last slide is showing a system that would run in cure mode 8 hours a day. And cure mode is typically, when you're looking at a heating only system, cure mode is typically the one that producers use the most energy on. So you can see that the savings are substantially greater. Again, at the 100,000 CFM size, you're looking at a savings of 40,000 CFM in Dallas versus north of $52,000 a year in Chicago. And with that, I think Geoff will be reviewing some other requirements that need to be considered when we're looking at recirculation for your process.
All right, thanks, Brian. Right, so I want to start discussing, or now that Brian has emphasized the benefits that a recirculation spray booth may offer, we want to have a discussion about the additional features that are necessary in order to safely do it. These features are driven by requirements in the codes and standards that are enforced in your jurisdiction. These codes and standards will likely be NFPA 33, standard for spray application using flammable and combustible materials, and the International Fire Code in the United States and the National Fire Code in Canada. It is the requirements of these documents that we will be referencing in this discussion. But before getting into the features, there is information that is needed in order for us to determine if and how you can recirculate the exhaust from your spray operation. Since we're dealing with worker health and safety issues, we need to review the safety data sheets of the paints, solvents, and cleaning materials that may be used within the spray booth. The safety data sheets will give us information such as how much flammable or combustible liquid is present in the paint, the lower flammable limit of the mixture, and a breakdown of the different ingredients in the paint. We also need to know how much you'll be spraying. What we're looking for here is the number of spray guns and the spray rate per gun, often given in ounces per minute or cubic centimeters per minute. This will give us the maximum rate of material that will be introduced into the system during your spraying operations. So why do we ask for this information? The NFPA 33, the International Fire Code, and the National Fire Code of Canada require that spray booth ventilation systems accomplish 2 things. First, confine and remove vapors and mist to a safe location. And second, to keep the concentration of the vapors and mist in the exhaust airstream below 25% of the lower flammable limit. So we ask for this information because the type and quantity of materials will be used to establish the minimum fresh air rate into the spray booth to ensure we do not exceed the maximum concentration level allowed. If this minimum fresh air rate is less than what you would normally be provided in a conventional spray booth, then recirculating some portions of the exhaust may be possible. So to highlight the requirements, I thought we'd run through an example. And apologize in advance, there's lots of numbers, but bear with me. Say you have a spray operation that will be conducted in a Crossdraft spray booth that is 18 feet wide by 14 feet high by 60 feet deep. Typical air velocity in a cross-draft spray booth is about 100 feet per minute. At these dimensions and air velocity, the total flow rate through the spray booth would be 25,200 cubic feet per minute. We're going to say the spray operation takes 2 painters, each with a spray gun capable of 12.8 ounces per minute, and that the paint they are spraying is 50% solvent. After we do all the math, this works out to about 0.1 gallons per minute of solvent being released during spray operations. So paints involve all kinds of solvents, but to keep this example simple, we're going to use what we'll call a typical solvent. The typical solvent in this case has a lower flammable limit, often referred to as LFL or sometimes LEL, of about 1% in air, and will generate approximately 25 cubic feet of vapor per gallon. This means that 1 gallon of solvent evaporated and mixed in 2,500 cubic feet of air is at its lower flammable limit. So to be at a concentration of not more than 25%, we would need a minimum of 4 times as much fresh air, or 10,000 cubic feet per gallon of solvent released. Therefore, with 0.1 gallons of solvent being released per minute in this example, we would need a minimum of 1,000 cubic feet per minute of fresh air to ensure that at steady state conditions we would not be exceeding 25% concentration in the exhaust. So I'll come back to the example, but I think this is a good spot to pause and discuss another feature of recirculation spray booths. To allow recirculation, the concentration in the exhaust must be monitored by approved equipment. This equipment monitors the flammable concentration and is interlocked to shut down the spray application equipment if it detects a concentration greater than 25% of the lower flammable limit. The equipment is calibrated based upon the material sprayed, which is another reason why we ask for the safety data sheets. The information contained in them is used to select the appropriate calibration gas. So back to the example, if you remember, we had calculated that we needed a minimum fresh air rate of 1,000 cubic feet per minute to give us a concentration of 25% of the LFL in the exhaust. However, if we only introduce this amount, we would be operating at the same concentration level where the monitoring equipment is required to shut down the spray application equipment. So to avoid shutdowns due to operating right at that limit, we often design recirculation spray booths for an exhaust concentration range of 5% to 15% of the LFL. The upper end of the range is common for unoccupied spray operations such as robotic spray booths. But since in this example the spray booth is occupied, we'll use 5%. If the minimum fresh air flow rate is, as we calculated, 1,000 cubic feet per minute at 25% of the LFL, then it would need to be 5,000 cubic feet per minute at 5% of the LFL. So now we have a booth designed for 25,200 cubic feet per minute through the spray booth, and we only need 5,000 cubic feet per minute of fresh air to be below 5%. And through sheer coincidence and a great effort on my part to make all these numbers work out just right, this example works out pretty close to what we often refer to as an 80-20 recirculation spray booth. This is where 20% is fresh, uncontaminated air, and 80% of the air leaving the spray booth is returned back to the booth. Total flow rate, as Brian had mentioned earlier, through the spray booth is unchanged. We still have 25,200 cubic feet of air. So this example primarily focuses on the features designed to minimize the fire hazard associated with recirculating flammable vapors. For occupied spray application operation, there may be additional factors, such as acceptable exposure limits based upon the chemicals in the paint you're using, and suitable personnel protective equipment. Both of these may affect the amount of fresh air needed, or could ultimately result in the recirculation not being a viable solution. The last feature for recirculation spray booths we want to cover is filtration. As you know, exhaust filters serve to reduce the amount of particulate that could escape a spray booth. For recirculation spray booths, a recirculation particulate filter is required to ensure that little to no particulates are returned to the spray booth or deposited in the recirculation ductwork. NFPA 33 defines a recirculation particulate filter as a single filter or a set of filters capable of removing more than 95% of particles in the 0.3 to 10 micron range. This efficiency requirement is not the same as arrestants. There are filters with stated overall arrestants greater than 95%, but these types of filters typically do not remove 95% of the particles in the range required for recirculation. So for recirculation filters, when you're looking at the performance characteristics, it's important that you look at test data that is based upon the method outlined in ASHRAE 52.1. Brian and I hope we've provided you with useful information today to determine if a recirculation spray booth meets both your production needs and your safety requirements.
If you liked our presentation today, please like and subscribe.
Thank you for your time and have a great rest of your day.